So we're in day 2 of geometrical application problems. This is a very, very, very common type of problem, and I want to make sure we just see how to do it and sort of things we need to be able to write. It says, example, a rectangular poster is to have side margins of 2 inches, top and bottom margins of 4 inches, and 50 square inches of printed matter. What are the dimensions of the poster of least area that meets the specifications? Okay, what I'm going to try to do is to go over here and we'll see what we can do here. I'm going to draw a picture first. They wanted to have a rectangular poster, so I'm just going to draw something that's sort of rectangular to the best I can. There's printed matter on the inside, so I'm just going to put some printed matter on the inside. I'm going to call this L. I'm going to call this W like this. They told us, I think, that there were 4-inch margins at the top and bottom, so there's a 4 up there and a 4 down there. There were 2 inches margin on the left and right hand side. Now what did they tell us? They said the printed matter had area 50. So up here, I'm just going to write down for later reference, LW equals 50. Now, that's a constraint, right? I mean, the 50 doesn't change. What they wanted to do is minimize the area of the whole poster so it used the least amount of material. So up here I'm going to put a little area, because that's what we're minimizing. Now what do I need? It's not going to be L times W. It's going to be this full length times this full width. This full length is L plus 8. So I'll put a little L plus 8 right there. The full width is going to be W plus 4. And that's the function that we're trying to optimize. So once I have that, I'm not going to need the picture anymore, I think. Remember, the goal of optimization is to try to use calculus. This is the thing I would want to take the derivative of, but I can't take the derivative of it because there's 2 variables. And the usual procedure is to go over to your constraint equation, solve for a variable, plug back in, get a function of 1 variable, and start doing calculus. So this is what we're going to do. I'm going to solve for W. It doesn't matter which one I solve for here. Sometimes it does. This one, it absolutely does not. So I'm just going to write W equals 50 over L like that. And I'm going to plug in for W. Now, I'm going to write A over here with one more thing. Once I plug in for W, there's all the W's are gone, and all I'm going to have is a function of L. So I'm going to put a function of L like that. All right, so I'm going to get L plus 8. That didn't change. I'm now going to write 50 over L plus 4. Now at this point, what I usually like to do is look for a closed interval. All I know though is that L is bigger than 0. It can be actually extremely big, which is not good. That means we can't finish with a table. We're going to have to make a sign chart or worse, maybe an entire graph, but we'll see. Meanwhile, I want to take the derivative of this. My options are either to use the product rule, which I'm not going to do, or multiply out first and just use the power rule. That's what I'm going to do. So I'm just going to keep writing equals until I actually get something I want to take the derivative of. I'm not going to FOIL, so I'm going to get 50 plus 4L plus 400 over L plus 32. Now I could take the derivative of that, but I don't like the way the 400 over L looks, and the 50 and the 32 I can combine. So I'm going to do that first, and we're going to get 82, which I'm very good with that, and 4L, that's good, plus 400 times L to the minus 1. This is now an extremely easy thing to take a derivative. So let's take the derivative. I'm going to write down A prime of L like that. I'm going to get 0 plus 4 minus 4 L to the minus 2. Now remember, we're supposed to start looking for critical points, but almost always when you start looking for critical points, you want to take your derivative and you want to write it as a single fraction. So you can set it equal to 0 by setting the top equal to 0, and you can find where it's undefined by setting the bottom equal to 0. So we're going to rewrite this as a fraction before we start any of that. So this is going to be 4 minus 400 over L squared. That's not a single fraction yet. I'm going to get a common denominator. So this is going to be, what is this going to be? This is going to be 4L squared minus 400 all over L squared. Looking better. I'm going to factor this. So what's this going to be? I think I'm going to put it at the top because we're going to have to make a sign chart anyways. So we're still just simplifying the derivative. Going to the top. This is going to be, so this is A prime. This is 4 times L minus 10 times L plus 10 L all over L squared. Okay, erase the bottom. Now what are we supposed to do? We're looking for critical points. So we want to set the bottom equal to 0. If we put that in red just so it looks like different work. Yes, I'm going to set this equal to 0. And this is when L equals 0. If I set the top equal to 0, running out of room here, I'm going to go like this. So this is when L is equal to plus or minus 10. So if I start making a number line, it looks to me like I'm going to have 3 different numbers on it. However, we know from the picture that L has to be bigger than 0. So when I start making my number line, we don't have to worry about minus 10. We don't have to worry about 0. So there's only going to be one number on that entire number line. I'm going to go like this. I'm going to go like this. L is going to go like that. A prime is going to go like that. A is going to go like that. Now there's 0. I'll cross it all off. I know I'm supposed to put 10 on there. And how do we do sign charts? Once you actually find the numbers for your number line, you're supposed to take those numbers and plug them back in. When I take 10 and I put it back into the derivative, I get a 0. That's good. I now need a number between 0 and 10. I tend to like 1. It might not be the best answer here, but we're going to see. When I take L equals 1 and put a 1 here and a 1 here, I get negative. When I pick a number bigger than 10, how about 20? So I don't have to think hard about that. When I put a 20 here and a 20 here and a 20 here, I get positive. Now, how does this sign chart work? Let's see here. Don't have to worry about anything out here. When the derivative is negative, the function is decreasing. When the derivative is positive, the function is increasing. And so what we can see, because there's only one critical point, this isn't doing any more wiggling. It always comes down to this point. It always goes up to this point. We can see that the function a has a global minimum when L equals 10. So we'll write this down here. A has a global min. When L equals 10, L equals 10 like that. Now I don't remember what they asked for and I don't want to go back, so hold on one second. Let's find the things that they might have asked for and we'll put them in like this. I know I already took care of that. And then let's see here, what do we also get? We're going to get W equals 5. And then the dimensions of the whole page, here, let's do it over here just so I have a picture, right? Let's see, L is 10, so that's going to make this side 18. W is 5, that's going to make this whole side 9. And I think we've answered all the questions they possibly could have asked. So there we go.